if I print the red part and the mask moves and I print the green part here, then the red part is going to shield the red region. So this is the source and this is the drain. I have a channel here. Okay, but what about here? What's happening here? شو الكاتاستروفيك فولت اللي صارت هون؟ هون كل السورس وكل الدرين are separated by the channel region which will be on or off حسب السويتش حسب الجيت voltage. Here what happened in this mistake in this fault? I have N plus I have N plus I have N plus يعني إذا رحت حطيت هون VDD وهون ground أو vice versa هون ground وهون VDD, what is going to happen if the gate equal to 0? لو ما في channel what do I have?
circuited يعني?
I have
it's
connected. I have connected high carrier density of N plus. Okay, and it's going to be shorted. Okay, great. صح? So excellent. Okay, so this catastrophic error means I don't have a transistor. I have a short. This is why when we typically fabricate, we require that there is an extra extension, okay, of the poly حتى any jitter, if it shifts little bit, we are still covered, okay, we are still covered. So هيدا الأوفرلاب, okay, the overlap هو قديش في عندي extension beyond the real region that I need, okay, is one of the rules that we care about. Okay, so we don't have to dwell about this because you're not going to dwell on this a lot, but this was just meant to explain why we have rules. هلا مثلا هاي it is يعني we need to know it لأنه بعدين we will give you a table for capacitance. حنصير نقلكم capacitance per unit length مثلا for metal 1 C per unit length will give you tables for metal 1 running over field oxide, okay, running over field oxide مثلا لنقول is equal to 70 femtofarad per micrometer length. What does this mean? And we'll take this later. It means that if I have a piece of metal 1, okay, so if I have a piece of metal 1 whose length is 1 micrometer, okay, and it's running over field, شو هو الفيلد؟ ما أنا عندي layer هون metal 1, metal 2, metal 3, 4, 5, and 6, okay? And between metal 1 and the wafer, I have oxide. So I have oxide. So I have insulator. So this is metal 1 and the capacitance بالنسبة للسبستريت لأنه السبستريت is grounded. So it has some capacitance per unit length, okay? نفس الشيء in a similar fashion, if I happen to have a piece of metal 6 running, قديش هيدي هي عندها كمان capacitance في multiple layers, many layers of oxide, وإذا ما مارق تحتها ولا other metal بالنسبة لها للسبستريت, so it will have some capacitance. But what happens to metal 6? It is far, right? So metal 6, the capacitance per unit length over field, يعني if there's nothing else below it, I just have a long metal 6 wire, it may have maybe lower, maybe 40 femtofarad per micrometer. ليه؟ لأنه the distance مش هي C is equal epsilon A over D. This is the first plate اللي هو metal 6 and this is the second plate اللي هو substrate لأنها هي الground, and the insulator distance represents D. So the higher I go up in the metal layer, the more insulator or more layers I have between it and the ground, and therefore the capacitance with respect to ground, if nothing is in between in the way, decreases لأنه distance is further. هلا طبعا it is not only this, metal 6 may have a larger area, يعني قلنا نحن الوايرز بيصيروا wider and bigger as they are higher, so the A may be larger, per unit length may be larger. So هيدي لأنه ال A, what is A? It is W times L. So if the width is larger, this means that I have a bigger surface of capacitance as opposed in metal one, it might be a smaller surface. So هون ال capacitance per unit length parameters بيفرقوا شوي. يعني عند ال distance بعدت, it is further, but the width of the wire will be bigger لأنه I'm dealing with upper layers which I need for robustly sending the signal over the whole chip. So هلا don't worry about the capacitance, بس عم بعطيكم look ahead بس لأنتم to be comfortable with why am I showing you those different layers, to show you that as I go up in the layer I have more insulator, okay, between it and between the ground or the substrate. هلا as we agreed there is contact between metal 1 and the poly, or between metal 1 and let me just erase these to explain what I want to show you here. So here, if we look at this region here, if you notice, he's showing you that there's a contact from metal 1 to the source or drain regions, and there's a contact also between metal 1 and the gate material. And the gate material بدها تكون little bit above the source and the drain as we agreed. Okay. Now between metal and metal we have what we call vias. نبلش نسميهم via 1, via 2, etc. These are just pins, connections from one layer to another. The constraints or rules about them are how wide it should be. We don't need to worry about that and stuff like that. Okay. So أهم شيء بس نعرف إنه عندي metal layers. The higher I go, the further I go from the substrate. That's all we need to know from this slide. Anybody has any question?
Yes, Professor, please. What's the difference between a via and a contact in this context?
ماشي. الفيا هي بتكون بين metal وmetal. اوكي. الكونتاكت هي بين metal وsource drain or metal وpoly أو gate type. Okay. The difference in terms of fabrication is nothing, but we use it to differentiate لأنه rules عليها it has to be designed more sophisticated لأنها it's at the smallest layer, so we call it contact.
Okay. Thank you. And you said something about the W getting larger as we go up?
How we will talk about it later, but the reason why it becomes larger لأنه أنا if I have a big chip, let us say 1 millimeter where أو several 1 centimeter عندي wire going 1 centimeter versus at the gate scale عندي wire going 10 micrometer. The lower ones I route them at the lower wires, but the big signals that go long distances over the chip, كيف الhighway on the map, they have to be wide, they have to be big, and they have to supply the signal to many locations. So we don't want them to have high resistance. If they are wider and thicker, they allow more. كيف pipe of water, the main branch is big and then the little branches are small. نفس الشيء. The resistance will be smaller, and so as we go down, the little pipes become smaller and the resistance becomes bigger. لأنه I'm sending them short distances. Okay?
Thank you very much.
Okay, thank you. Anybody has any other question?
Professor, at what layer is the heat generation the greatest? At the bottom or at the top?
هلا depends on the chip. Typically in the lower layers لأنه we have dense metal 1 and wiring, and maybe the VDD network is on metal 2 typically or metal 3. هلا the top layers بصير عم نعمل routing for the clock and then it goes down, and even the big supply goes from metal 6 down to the lower metal layers. But typically the lower, where you have the activity of charge and discharge is where you get most heating. And it is most dense, they are closer to each other and the resistors are smaller. Okay, but it depends on the design of the chip. Okay?
Okay, thank you.
Okay, thank you. Okay. هلا here we are showing the question which Imad asked about before, which is the through silicon via. هيدي بس a new technology, and we're not going to work with it. We are saying that we have 3D chips, يعني I stack multiple chips on top of each other. So I will have the processor designed in one location. I will have the DRAM, for example, designed in another location. And then I try to connect the different layers to each other by drilling through the wafers, and this is a new technology that we will not يعني بس هيك FYI. Okay, طيب great. لكن عندي set of rules. Rules is going to tell me, well, what are the layers that you are using? It is going to tell me, well, within the layer, if I have 2 metal wires or 2 pulleys, what is their minimum width so that I can print them, ما يطلعوا مش printed. What is the distance between two, the closest distance I'm allowed between 2 entities of the same material so that they don't end up shorting. And maybe the area, in some cases, مثلا the contact area, what it should be, لأنه it should not be smaller than a specific area, so that it, لأن هي pin نازل نزول مثل البايب كمان، ما بدي resistance تاعنا يكون too small إذا it doesn't let in too much current. And then between layers, so this is within the layer, okay, and then from layer to layer, يعني an interlayer, from layer to layer, as we saw. For example, the case of the poly and the diffusion, they have to have some overlap, some extension. مثلا, if I'm putting poly, let us say that I have one transistor here and I'm putting its poly, and then I have another P transistor here. I want to make sure that there is a distance between this poly of transistor 1. يعني it has to overlap well with this, but it has to be far from the second transistor, right? So these are the distances, the enclosures, and other rules. It's complex. We don't have to worry about all of them. We'll just study the basics and the distances between the metals, and later how this affects the capacitances, okay? هلا, what matters for us in all of this, like as a high level, is that there is something called the transistor scalable design rules. What do I mean? يعني I have a processor, a company like IBM or Intel is investing in designing a 32 nanometer processor, it built مثلا the inverter, and the inverter had L equal 32. And it has all these other gates, so and the chip فيها million transistors, and now they want to move down to 24 nanometer. Should they redesign the whole rules? No, what they said, let us make some rules and build a grid. And this grid, for example, is going to be مثل الجريد اللي بتشوفوه على الجراف sheet. Okay, it has grids. Okay, so it is going to say that this grid, okay, and let me erase it because it does not look good, that this grid that I am going to draw on top of this transistor is going to be function of L. يعني أنا إذا عاملة distances مثلا لنقول هيدا الويدث هو عبارة عن 3 grid points. Okay, what I can do to scale is I can draw the same transistor, use the same transistor drawing, okay, but instead of those 3 grid steps being, let us say 100, I can say now they are 60. So what did I do between here and here? شو عملت أنا؟ يعني أنا إذا عندي mesh, okay, let us look at this like this. If in 32 nanometer I said the distance or the lambda of one block is 16 nanometer, then for the same drawing in 24 nanometer, if I want to adopt the same, what should be this lambda or distance? شو بتصير؟ إذا هي بال 32 كانت نص ال 32 بال 24 تخلي رسمة الترانزستور هي ذاتها and not change it to keep the same drawing. What should lambda be in 24 nanometer?
12.
12, right? Okay, so now I had a grid or a drawing that had some circuits built based on the 32, and I can reuse the same grid or drawing, but now when I interpret it to the circuit, I tell it, use your grid point from point to point distance, instead of being 16, use it as 12. Let's see what this means on this next slide, and it will be clearer. يعني هون it is telling me the simplest thing that I need to draw on the chip is a poly piece with a channel length L. If I want to migrate this design, if I build it in 32 nanometer, L is going to span 2 grid points, Okay. طيب, if I want where the grid point is 16 nanometer, if I want to migrate this design to 24 nanometer, I can use the same drawing, the same layout to build the mask, except that I'm going to tell the mask rescale, okay, such that your grid point now is 12 nanometer. يعني this way I can move one design to another by changing the scale or the interpretation of how to build the mask from this layout, but keeping the layout. طبعا, some portions of the design may need custom design, but the design, they are trying to make the design rules scalable. Okay, so they make the design rules scalable. يعني أنا if I draw L equal to 2 lambda, my drawing in 32 nanometer will be interpreted to 2 times 16, and my drawing in 24 nanometer will be interpreted to 2 times 12. Okay, so now I can take the same layout, but then throw it and start from scratch. Okay, so this is just terminology. And somebody said, let me reuse this layout which I drew in 32, but let me draw a grid on top of it and just say every 16 nanometer will now be counted as 12. Exactly مثل ما تشوفوا المات, not to scale, you can draw a bigger map. Instead of drawing a bigger map, they just tell you that your scale now, lambda, changed from 16 to 12 and so on, so forth. Okay, بدل ما نكبر الدروينج أو نصغرها, we just say the scale changed. Okay, so for you, what matters is that if we tell you that we have drawn a scalable design rule, for example, if we say that we have a transistor, okay, of 32 nanometer technology, where the W is 3 lambda, for example, and what is W? شو بنجي بنقول؟ I know that this is 32 nanometer. What do I know about L from this scalable design rule? That lambda is what in relation to L?
Half an L.
Half L. They agreed on it. So lambda is half L. أنا بال 32 nanometer, يعني it is half times 32. Can I know my width now?
Yes, because we now have lambda.
Okay, so we know what L lambda is. It is half L, half 32. We know it is 16. بعرف ال width is 3 times 16. I'm done and I move on. Okay, so all we want to know is that we're drawing it to a scale whose unit is lambda and lambda is half L. Okay, that's what we need to know for our purposes. Okay, طيب. Great, let me go to the next slide. Now on this slide, we are going to define the different parameters as function of lambda. يعني in the metal layer, we will tell you that the width is 3 lambda, that the distance between two wires in the same layer is going in metal 1 is going to be 4 lambda. So now you know how to interpret these definitions. Okay, why we want to have a minimum separation between objects in the same layer? So that I do not short them when I fabricate by mistake. كرمال for the resolution of my printing to be on the safe side. Okay. طيب هلا we're going to come. Yes.
I'm sorry, but what do we exactly mean by objects?
Okay, this is an object. It's a wire.
No,
can be
does
a
it include
contact.
everything? يعني wires?
Yeah, it can be a contact. It can be a polyline. It can be a metal wire. It can be a source drain diffusion. These are the different entities that we see, right?
بس نحن مش مجبورين ب certain specs such as let's say
right.
whatever.
These are the design rules. That's what he's telling you. He's telling you if you are on the layer of metal 1, if you want to draw the wire has to have a minimum width, okay, of 3 lambda. It cannot be shorter, ما حطيناها هون لأنه نحكي عن الاريا. It cannot be shorter than a certain distance, and it cannot be close to any other wire closer than 4 lambda. Before you place إذا أنا عندي wire 1, before you place wire 2, you have to adhere to this rule. Okay. Okay.
Thank you.
Great, thank you. طب هلا هون عنا now we're going to talk about the stick diagram, and the stick diagram is important for us because we're going to deal with the logic gates again using those stick diagrams. And we're going to revisit the NAND, the complex CMOS gate using the stick diagram. What does the stick diagram tell me? The stick diagram tells me before you start to print the layout on the simulator and the tools, just I want to know a sketch how you want to lay it out. يعني مثل ما الاركيتكت بيعمل small map هيك a little sketch of the house and then he goes to the real tools and stuff like that. We want to know how to place our transistors and how to make the area compact. So let us see what is the stick diagram. This is the inverter. Let us see how we map the different entities of the inverter together. So let me draw it for you. Okay, let us draw it from scratch, and then we will show you how it maps here to this layout. Okay, so I have an inverter, and the inverter is a PMOS. Okay, and an NMOS. It is connected to ground. This is VDD, and this is VN. Okay, so let us call this VN as A, V out is B or out. Okay, and this is VDD, and this is ground. Okay, I have labeled all my nodes. Typically, when I draw a stick diagram, I want the gate to be compact. So I assume to connect, if we connected the layout of the inverter, the VDD to VDD and the ground to ground, first I'm going to draw the lines for VDD and the lines for ground. Then I am going to draw a line for the NMOS transistor to represent its diffusion region, and a line for the PMOS transistor to represent its diffusion region. Okay, now in this circuit I have the same input and one transistor by one transistor, so the same poly input can connect over the two. شو عم يعمل هيدا لما I send it from the NMOS to the PMOS? What is happening? At this intersection I'm creating the NMOS transistor, and at this intersection I'm creating the PMOS transistor. يعني I'm creating this from this intersection here, صح? And I'm creating this also from this intersection here. So all I'm saying is that really I have an NMOS and I have a PMOS diffusion, and I am connecting, I'm sending the same input. مش هو لازم يكون A sent to both of them؟ بس ما أنا I can send A to both of them. Here it will create the PMOS device, and here it will create the NMOS device. Okay, so I'm just stating that these two have the same gate. Clear? Okay, so this is the same gate A. Now, what do I need to do to have the connection finalized? What do I need to do to have the connection finalized? شو بعد? What do these transistors miss?
Contact.
I have, exactly, so I need to send contacts to connect what? To connect, let us see what nodes are still not connected. I need to connect first this node to VDD. So I will connect this node to VDD. I need to connect this node to ground. So I'm going to connect this node to ground. And I need to connect this node of the transistor to this node of the transistor. So I need to put a contact here and a contact here. And I need to connect them together to give me the out node. Okay, يعني I sent a metal to the diffusion of this node, and I sent a metal to the diffusion of this node, and I found what my output is. Okay, is this clear? For yes.
Sorry to interrupt you. كمان بدنا contact بين البولي يعني الجيت وال.
هلا بعد ما بعتنا. If we want to send the signal A, if I want to send the signal A from somewhere else, I will send a metal with a contact that will connect to the poly which is going to the two transistors, right?
وبين البولي والترانزستور.
لا، بين البولي والترانزستور there is no contact. When we draw the transistor, we will have the diffusion regions. اتفقنا, right? This is my substrate, and on top of the substrate, what do I put? I put oxide, معنى نفس الcolor هون مساقة, and then I put the gate on top of it. So I just run the poly over the diffusion region. I don't have a contact there. The overlap هيدي بنسميها the overlap of poly and diffusion تعطيني transistor, right? It runs over it. Okay. الكونتاكت بيجي من الميتال 1 عنده كونتاكت على البولي، أو بده يجي من الميتال 1 عندك كونتاكت على source drain of course لل two types يعني للأنموس للبيموس. اوكي clear؟
اوكي thank you.
perfect. يعني هيدي حتطلع هون حنربطها بكونتاكت ليفيدني على الميتال على الفينيديل. اوكي طب great. So now let us see. Yes Mario.
Professor?
Yeah.
You're making it seem as though if we put the gate on top of the like the regions, the doped regions, then it work. But shouldn't, like in the drawing on the left, you say there shouldn't be anything under the gate, like there shouldn't be an N
There
well.
should be oxide. هلا ما فينا نرسم الأوكسايد نحن.
Right, no,
إيه
but
and
draw
for
the
the
green
PMOS, for the PMOS, yes, there is an annual here. بس نحن we are just drawing the whole thing as the combination of the diffusion and the annual. That was your question, Mario?
I'm not exactly. So like
No,
in the,
ask me.
in the drawing on the right with the with the orange rectangle, when you draw the rectangle, you draw the gate on top of it. It makes us think that underneath the gate there is some doped P.
Okay. Let me go back to this. This is from the way we fabricated. Let me come back here. Under it there is no, and it should be highlighted, but let me show you here. Here when we looked at this, the way we fabricated is first I place the gate. Okay, so it gets filled. صح? And then I'm going to bring a rectangle of poly of diffusion, but really it's going to fill here and here. So أنا هون بس عم برسم what I'm drawing here as the rectangle. I'm just drawing the what we call the active area, which means the area where the transistor is going to be drawn. But really the filled parts, you're right, it's only this and this, and the filled part, and this is poly. ما في هون. I don't have active under it. I don't have something like this, definitely not. Okay, so if I go back, this is what you were asking about, Mario, right?
Right, exactly.
Okay, so if I go back to the figure on the lower right, I need to fill the red fully and strongly and say it is filled here وحواليه في green. يعني أنا بس I'm sketching the location where the source and drain will flow. Okay, is this clear now? Okay. So let us now see what they drew for me here. So really, yes, he said I'm going to make a line for the PMOS and a line for the NMOS diffusion. And then I'm going to represent the input as one stretch of poly that is going from the two transistors, and they have the same input. And of course, the input will arrive from a metal signal and will go down into the poly, tap into the poly. And then one node of the PMOS will connect to V, the other to output, and one node of the NMOS will connect to ground and the other to output. So it's very important for you to be comfortable how to draw the stick diagram of the inverter. First, it is dimensionless. Then it really explains to me how I'm going to draw more complex gates in a compact fashion before I worry about the different design rules and how wide and how thick the wire. يعني بس the connections, the node connections. Okay, so let us look now at this. Why do I need the stick diagram؟ لأنه I'm aiming for layouts to be regular and compact. يعني على طول بدي ال VDD while running, the ground while running, always printing the annual or the P on this line, always printing the NMOS below, always having vertically spread and shared inputs between the different transistors. So let us see, for this to happen, I need a lot of regularization, and the Euler path along with the stick diagram will help me achieve this. So let us look if I have a NAND gate. So I have a NAND gate, and in this NAND gate, what is it? What is the expression for the NAND? The expression for the NAND is Y equal AB bar, right? So we draw it as a stack of A and B in series, and in the PMOS they are in parallel. Hello. To be able to guarantee that whatever poly input goes to the NMOS will have the corresponding transistor. يعني فيني اطلع فيها vertically وفيد the corresponding transistor. يعني هيدا B وهيدا B. ال PMOS with the same poly stretch. We need to aim at this form. Let us see how. يعني أنا, if I am looking here, what is the order of inputs that I visited here? B, then A, right? And the order of inputs that I visit for the PMOS, B, then A. So I want them to be visited in the same order. يعني the PMOS for B first, and then the PMOS for A. The NMOS for B first, and then the NMOS for A. This means that when I come to the schematic, I want to create a path here that will visit B first and visit A first. يعني أنا, if I start to visit the transistors, let me assume they are houses, I'm going to go in the path B to A, and I can find a similar path on the PMOS that starts from VDD and goes through B and then visits A. Okay? So let us label the nodes. This is a ground. This is node 1. This is node Y. Okay? So on the NMOS path, okay, if I want to write the NMOS path, I am really visiting, I'm going to write the nodes in all the nodes. I'm visiting node ground, right? Then I'm visiting transistor B, I'm visiting node 1, I'm visiting transistor A, then I'm visiting the output node, right? And B and A represent for me the poly, right? Now, when I want to look at how I visited the PMOS path, let us see what we visited there. So for the PMOS path, I started from here. So I visited VDD, I visited transistor B, then I visited node Y here, then I continued my circle, I passed by transistor A, then I visited VDD again. So this means that I visited, sorry معلش لو أنها غلط, I visited B and I visited, then I visited the poly of A, and I visited this, then this. Okay, so do you all agree how my path is going? So it went from ground to B to 1 to Y, and it went from VDD to B to Y to A to VDD. Okay, so let me, with this given, okay, with this given, let me show you how we would draw the stick diagram. Let us see how we would draw the stick diagram for this circuit. Okay, so let us see how we draw the stick diagram for this circuit. Hopefully deleting this will not delete everything. Sorry, 1 second حتى تكون clear for you how we draw now the stick diagram. So, let me see. Since I have one path, since I have, well, I'm going to write them again, it's okay. So أنا عندي هون قلنا VDD B, Y, we visited the transistor A, then we came back to VDD, and here we had the ground, then we went to B, then we went to node 1, and then we visited transistor A, and then we visited node 1. So if we want to follow the same way we drew the stick diagram for the inverter. I'm going to put VDD. I'm going to put the ground here. I'm going to put the P diffusion and the well here. So this is the P. I'm going to put the N diffusion here. And I'm going to see now, well, I'm going to have, let's see what we can do. And then we will talk about the magic of this. I'm going to put a strip for B. And I'm going to put another strip for A. How many NMOS transistors did I do here?
2.
2. And how many PMOSes? 2 also, right? لأن عندي overlap between red and PMOS type and red and green, which is NMOS type. Great. Let me see what does this enforce here. شو عمل لي enforcing هيدا connection of the one strip of the N? What did this enforce here between this node, between A and B? Is it connected? Is it telling me there is a connected node between A and B automatically?
Yes, supposedly.
Yes. So هيدي continuous strip لما أنا مشيت عم بلحق أنا a single path that will go through the diffusions. ليه؟ لأنه هيدا مشي بالسورس درين، قطع تحت الشانل مش بالسورس، قطع بالكومن نود وكفى عند الاوتبوت. يعني a single path that I can find is really representing. طبعا في عندي تشانل هون، سو هيدي هي تشانل ممكن تكون on ممكن تكون off محل حيقطعوا A و B. But this single path is telling me that when these transistors are on, I am going to have a single path between a ground and out. صح? And this single path is enforcing a connection between those two transistors. هلا بنحكي عنه بعد شوي. But let me now try to follow the path. يعني خلينا ناخدها graphics هلا بس. My path is starting from this node and it is visiting transistor B. So إذا اعتبرت أنا I was moving in my path in this direction, from what node did this go start? From what node did this path start? From ground. هيها. So هيدي حاجي أربطها بالground. صح؟ Then it went through transistor B. So قطعت بترانزستور B. Then it went through a common node. Do I need to do anything about it? This common node بين A and B, it is natural, it is called one, and it is naturally connected by the diffusion. حسب ما شفنا. هلا نشرح بعدين more detail. بس I'm just following the logic here, right? Is this connected? Do I need to do anything about it? No. No. طيب then I visit the poly of A يلي هو طبعا جاي فوقها للهاي. Then I visit the poly of A. Okay, so هي هالأي channel موجودة مرسومة. It can be on or off. Then I visit what node? Y. So أنا هيدي النود اللي هون. This node here I have to call what? Y. This node here I have to call Y. يعني هيدي النود هي هيدي النود من الترانزستور A اللي اسمها Y. Okay, so هيدا path, this path we already visited it. So I'm going to delete its route. هلا بنرسم البولي بنرجع بنظبطه. هلا what do I need to fill in? I need to connect the nodes. خلقت the two transistors. I need to see how I adhere to this path. Right, to this path here. طيب, this path here is really connecting, is starting from B, from this node, going to B, going to Y, and so on and so forth. So أنا إذا بدي أعمل a little bit this path, if I want to make a sketch where this path is going to go, it's going to go here, right? لما بتقطع B بعدين على A. The first node that is sees, the first node that it sees in this path, what is it? The first node that it sees in this path is what?
VDD.
VDD. So it is going to connect this source or drain of B to what? To VDD. يعني أنا بكون عبيت هيدي النقطة صح؟ طيب Great. Now we're moving to what? We are now at node B. عندي ال B. بدي روح على the other diffusion of B, which is what node? شو اسمها النود؟ دي من
Y.
تاني side Y. طيب وهيدي ال Y هي هون and it is a common diffusion بين ال A وال B موصولة هي naturally it is connected. I don't have to do anything. هلا I'm going to visit the gate of transistor A. صح؟ so حأجي عند ال gate of transistor A عندي إياها. Then the last node بعد ما أقطع ال A هي هاي. ما أنا قطعت ال A هلا طلعت لهون. So the last node is going to connect the source of A to VDD اللي هي هيدا الديفيوجن اللي بعده مش موصل. And this is going to connect the source of A to VDD. Okay, so أنا بكون هلا خلصت الباث يعني أنا بدي أمشي فيه من ال B لل A صح؟ بكون خلصت الباث بدي أمشي فيه من ال B لل A بال PMOS devices. Is this clear؟ طب خلينا نشوف شو عندي نودز. أنا ال A مظبوطة هاي راحت على ال VDD. شو في عندي نود بعد بدها تتوصل؟ عندي ال Y بالبي ستريب وعند الواي بالان ستريب. هدول هن نفس النود صح؟ right? So I need to create a contact to connect them to the same output صح؟ هو بيصيروا هلا connecting the node Y بين هالشقفة وبين هالشقفة خلقت وصلة بين ال PMOS path اللي رسمته وبين ال NMOS path يلي رسمته. اوكي حدا عنده سؤال؟ I'm going to erase بس الرسمة على هيدا اللي رسمناها فوق هيدا and please let me know if you have any questions. Later we will talk about the traditional way, but first what I want to know is that you were able to follow that if I predefine for you a path that visits A to B and a path that visits B to A in this order and a path in the PMOS that visits B to A in this order, and if I draw the poly in red على hot two strips أنا بقدر I can follow the path and I can connect my nodes in the stick diagram. Is this step clear? Anybody has any questions about this step?
Professor, systematically withdraw the track from VDD to ground bil PMOS و bil NMOS.
Systematically, I divide the P network alone. I look at it alone. I try to find a path that is going to visit all the transistors only once. Okay, so هيدا بلش من هون وكفى عند ال A صح؟ I want to visit. I need to have a starting point, right? This is my starting point. I want to visit all the transistors only once. ليه؟ لأنه أنا I want to apply the poly once لكل input صح؟ So I want to visit each house or each transistor once. So if I start from VDD, one possible path is BA بالpull up صح؟ So هاي بتكون مين؟ LP. Now my second objective is to look at the pull down network, okay, and visit the transistors. Can I find a path that visits the transistors in the same order? يعني أنا هون what did I find in the P? I found BA. Can I find a path that is going to visit the NMOS transistors in the same order B than A? Yes, this path is going to start from, sorry about this. This path is going to start from here, visit B, then A, and end here. Have I visited all the NMOS transistors with this path?
Yeah.
Yes. So this is our objective. So أنا لقيت path similar to the one in the PMOS. It visited all the transistors only once. ما قطعت على ال A will be up or more than once. And it visited them in the same order as the NMOS. So this means because it visited them in the same order as the NMOS, I can put the stretch of the poly for P and I can put the stretch of the poly for A. Okay, now What nodes did this path visit? هيدا it visited the source node of B اللي هي كانت ground اللي هي السورس للB صح؟ and then it visited the drain node of B اللي هي كانت 1 right? and then it went over transistor A طبعا هيدي هي common node and then it visited the drain node of A صح؟ يعني if I want to pardon me if I want to clear this and next time we can talk about it more if I want to explain this in another way well this really visited source B right then the transistor itself then the drain for B then the source for A right and then A then the drain for A بس نحنا we prefer to name them by the real name يعني هو قطع أول شيء على الجراوند صح then على الترانزستور then على common node 1 right then على which is common to A and B then on node Y right so this was a ground B1 transistor A and then node Y pardon me okay so is this clear? So we'll talk about it more
Yes.
next time, but I just wanted to give you a beginning feeling of it. Okay, so on Monday, inshallah, we continue this and then we can look how it applies to other types of gates and take more practice. طيب, thank you everybody and I will send you emails based on what we discussed today. Take care. Bye.
Thank you, Professor.
Thank you. Bye.